Hello everybody and welcome back. So in this next lesson we're going to be talking about user-defined functions. So this is basically where, up till now we've been using functions that already exist in Vex and in Houdini. But we can define our own functions if we need to repeat some particular type of function. So this would basically be whenever we would need to repeat a block of code, because obviously if we didn't need to repeat it, there would be no need to, define it as a function and then run the function. Why not just write those lines of code? So generally you're going to want to do this when you need to repeat something, but sometimes you don't want to repeat only based on a loop. Within a loop, things are generally duplicate. Okay, you're running a certain number of times and you're applying the exact same block of code. Sure, you can have if and else statements inside of that block, so you can vary it slightly, but sometimes it becomes very difficult to get a very custom sort of application of a function within a loop. So sometimes this is actually exactly where you would use a user-defined function, is basically you create the function and then you can run it without having to type a giant chunk of code. You can just run that one function and it does exactly what you want again and again. Okay, so we're going to build a pretty cool example over here just to kind of show you how to do it, but also a cool example of when you would use this. It's not particularly used that often. Most of the time you're going to find that a loop or another type of block is going to do pretty much what you need. Just in general, I've found that on a daily basis I'm not really doing lots of this, and I wouldn't encourage you to go and constantly define functions, but there are certain ones, especially when you get really long complicated Vex snippets, where you'll find that actually defining a user-defined function is better. And I would like to interject here with a sort of a general rule when it comes to coding, or it's sort of like a guideline, is you should almost never be repeating any lines of code, writing the same line of code again and again. That's why loops exist, and that's why creating custom functions exists as well. If something is being run multiple times, instead you create a function for it. In that same way, if you, for example, were referencing like, a channel, maybe I, have a channel like here, foo, and I want to, set some value to be equal to foo, and then later I'm also doing some other thing, maybe running a function or whatever, and inside of here, I also need to reference foo. If ever you were doing something like this, repeated lines of code, you see here I have channel and a reference to the foo and then another reference here, you would not do this. You'd make sure that you store it in a variable and then later you just reference val. So essentially it all comes down to that same rule of never repeating any lines of code. Okay, it just keeps things neater, simpler, it's easier to make changes later, and it's just a good practice. Okay, so this is where these user functions are really useful. Okay, so I've got a basic sphere here and I'm just going to start typing some code. Now we're going to create the code first. I'm going to create the snippet as though we're just running it here, and then we're going to turn it into a function, and I'll show you how that helps us to do extra effects. Okay, so I'm running over primitives here, and essentially what I'm wanting to do is take each one of these primitives and kind of draw a new primitive where the new points are, somewhere along this edge, and then another one along this edge, and another one on this edge. And then I'm going to basically remove the original primitive, because I don't want there to be any overlapping geometry. And I'm going to connect all those points into a new primitive. And in that way, you'll see we actually get some kind of cool, we can basically rotate this like each individual primitive. Okay, so it's going to be quite a cool effect. So here we go. So I know that because I want to loop over my primitives, because I want to do it for each primitive, but what I need access to are the points. So I'm going to run the prim points function. sorry, prim points, it's because we want the array of the full array of points. Okay, remember prim point is going to return only one specific point. And 0 because I want to run it on my current geometry, and then I'm just going to run at primnum. Okay, and I'm going to store this in an integer array. So integer because it's the list of point numbers, and then it's integer points, and it's an array. So we put the square brackets. Okay, so now I have my prim points array. And I also, before we carry on, I want an empty array where I'm going to store my new points, just so that I can access these at a later stage. So I don't need to define anything here, just initialize it. Okay. So now we're going to loop across all the points in this array. So I'm going to run a for each. A for each because it's nice and convenient. We just feed it an array and it will loop that many times and return an index and a value. Remember, the index is optional, but in this case we are going to use it. So I'm going to define my index as I, my value as v, and then I feed it the array. Okay, so this is all inside of a block. Okay, and you guys should all hopefully be following by this stage, because we've done all of these functions and loops and all that type of stuff. So I hope you are following. So here what we're going to do is calculate the position of not only the point, the current point that we're looping over, right? But we also want to calculate the position of the next point. Okay, so let's start with a simple one, which is calculating our current position. This is very easy, so I'm going to store this in a vector, and I'm going to call it pos1, and we're going to run just the point function to grab a point attribute. 0, so my current geometry. We tell it what attribute name, so p, and then I need to know the which point number, and that is our v, because remember, as we loop over this array of which points are associated with this primitive, as we loop over, the actual value of that, so in other words the point number, is going to be v, and then I is going to be the index. So I will be, because there are 4 points in this primitive, it's going to be 0, 1, 2, 3. So as it loops 4 times, it's going to be equal to 0, 1, 2, and 3 in that order. But v will be equal to, well, different for every, for every loop. It depends on the point numbers that are actually attached to that primitive. Okay, and that's exactly what we want here, is the point number. So I'm going to put it v. Okay. The next position that I want is going to be called pos2. And this one's a little harder to calculate, but it's not too bad. So we're going to do the same thing, point, 0, and p. But now we need to know the point number that is next in this order. And keeping in mind that, okay, I'm going to just disable this so it doesn't error out, and I'm going to switch on my point numbers. So let's take this one for example. When we loop this the first time, I is going to be equal to 0 because it's the first loop, the first index of this array, and v is going to be equal to 71. Now I want to grab 72, which is just plus 1. That's easy to get, okay? But we can't just rely on plus 1, because when we're looping on 72 and we want to calculate the halfway point along this edge, so I will be equal to 1, v will be equal to 72. So then when I do 72 plus 1, it's going to give me this point, and that is not what I want. I want to figure out the next point in the order of points that are attached to this primitive. So I want to circle around. So what I need is the number 96. Okay. Now how we're going to do that is we're going to access our points array again. So this array. Okay. And remember, in the square brackets, we can feed whichever index we want to grab. And because of I, we know which index we're currently processing, right? In this case, when we're on this, it would be v would be 72 and I would be 1. And what we want is I2, okay? So we just give I plus 1, okay? Now this would hopefully be enough. But the problem is when we move on, okay? So in this exact case, 72, I plus 1 is going to work, because then it's going to give us 96. It's going to give us the next point, and then we'll just grab its position. And then when we go from 96 to 95, that will work as well, because v will be equal to 96, I will be equal to 2, because remember 0, 1, 2. So then we take I plus 1, so 3, and it's going to return this point number, and we'll grab its position. So again, that works. But here's where the problem comes in. When we want to go from 95, so here v is equal to 95, I is equal to 3, 0, 1, 2, 3. Now what happens when we go 3 plus 1? That's 4. Our array does not have index number 4. It only has 4 elements, which means that the indices are 0, 1, 2, and 3. We cannot just plus 1. But there is something that allows us to loop numbers, okay? And that is called a modulus function, okay? So I don't know if you will have ever come across this, maybe in your sort of arithmetic at school, but the modulus function is with a percent sign, so the percentage sign. And what this essentially does is sets the number at which to loop. So for example, if I say modulus to 5, then 0 will be 0, 1 will be 1, 2 will be 2, 3 will be 3, 4 will be 4, but then 5 will be 0. As soon as it reaches that, after 5 numbers, because we're saying modulus to 5, then it loops back to 0. So 5 will be 0, 6 will be 1, 7 will be 2, and so on. So then when we reach 10, it will be 0 again, and then 11 will be 1, and so on. Okay? So what we're going to do here is we're wanting to loop based on the number of points in the array, which is easy. We're just going to use our len function, remember, because it's grabbing the length, in other words, the count of the number of elements in the array that we feed it. So we're going to use len points, okay? And all of that goes inside of the square brackets, because we're in here, we're just feeding it which index do we want to grab. So in this case now, 95 is going to say I, which is 3, plus 1, which is 4, modulus to the length of the array, which is 4. So 4 modulus to 4 is 0. Therefore, it's going to grab index number 0, which will be point number 71. And it will grab its point position. And then it will measure the distance between this and this one. Okay. So this should be working. So now we are grabbing this whole argument over here is the in place of v. So we still need to end our brackets and put a semicolon. Okay. So there are our 2 positions that we've now calculated. And now what we want to do is calculate the position that is between these 2 points, right? So we're going to create another vector. I'm going to call it pos, because this is the one that we actually want to use. And I'm going to, there's a lot of ways that we can calculate the halfway point between these 2, but I'm going to use the lerp function, which is the linear interpolation function. And here we feed it just 2 vectors, so pos1 and pos2, and then a bias which is essentially, if it's 0, then the returned value will be equal to exactly pos1. If the value is 1, it will return exactly this. And if it's 0.5, then it will return halfway between these 2. So it's essentially a linear bias from this point to this point, which is exactly what we want. Right, so for now I'm going to give it a static value of 0.5. Later we'll put that in as an actual parameter reference. Okay. So now we will have calculated the position of these points. And at the moment, we're working a little bit blind because we actually can't see where these values are, but we're going to add a point now so that we should be able to see whether we've done this correctly or not. So I'm going to store my point. So remember, with the add point function, it does return the point number. So I'm going to store it as an integer called pt for point. And then I'm going to run my add point function. And in this case, I'm just feeding it 0, so I want to add to the geometry handle of the first input geometry, and then the position, which is just pos. Okay. And there we have it, right? It's creating all these points at exactly halfway between here. And you'll see there's actually overlapping point numbers. So you'll see these look a little bit messy because obviously this is halfway between these 2 points as part of this primitive, but it also is also halfway between these 2 points as part of this primitive. So there are actually 2 overlapping points on every one of these new midpoints. Okay, which is correct. That is exactly what we want. Okay. So now what we want to do is, well, before we move on, because we're going to want to create a new a primitive from these, and one of the easiest ways to do that is to just feed it an array of new points. So we might as well, since we've got PT and we're inside of this loop, is just add our point to this array. Okay, so we're going to just put append, because remember it's a void function, so we do not have anything returned from it. We just run the function, we feed it the array that we want to append to, so new PTS, and then we feed it PT just to append it to this array. So now as we exit this loop, this array will be filled with 4 new point numbers. Okay. Now outside of this for each loop, because we don't want to do it, for every single point, we don't want to do it 4 times, we just want to do it once. And we also want to do it once this entire array has been filled. So we need to do it outside of the for each loop, is we're going to create the primitive that goes between these 4 new points. So we're going to store this in a variable, so int prim, the same way we're doing with the point number, all right? Sometimes I do this, and then later I find that I'm actually not referencing the number of this new primitive or new point. That's okay. These variables take very little memory to store, so I would kind of always do it. But if you want to later, once you're done, you can go clean up and get rid of any that we don't reference. But you'll see here we are actually referencing PT, so we need it. It's generally pretty good practice. Okay, so we say int prim, and then we say equals, and then we're going to run the add prim function. Now again, we give it 0 because we want to add to our geometry handle on the first input. Then we feed it the type. Now this type is a string, and in this case, remember before we used polyline because we were just drawing vertical lines. In this case, we're going to be using poly because this is a closed polygon. So in other words, it will draw a line, an edge between each 4 of these points, and will encapsulate that with an actual polygon, closed polygon. All right. And then we feed it because if we stopped here, we would just have a primitive that's just sitting at the origin and would need to actually attach it to these points with vertices. But there's a shortcut, which is just to feed it an array of points, and it will create the vertices for us. All right. Now when I hit insert, you see the result. So here's our new primitive at every one of these. So it has worked perfectly. The only problem is there's now overlapping geometry. We've got this primitive behind and then this new one that we've created on top. All right, and that's not what we want. So all we're going to do is go and remove the primitive. Now remember, we're running over primitives. So our at primnum is this primitive. We're currently processing this one primitive. Even though we've created a new one, that new one is just held in memory here. Our at primnum is this one. So we can just go and remove it from our first input geometry handle. We feed it, at primnum. And then with removing primitives, we need to give it a third argument, unlike removing points. This third argument is a Boolean, which will basically answer whether we should remove the points on that primitive or not. So I'll show you. If we say 0, we'll experiment with the difference between this, but if I say 0, then it's going to remove the primitive, but it's going to keep the points. Okay, so you'll see there our point number 72 still exists, but we've gotten rid of the actual primitive. And if I say 1, then those points will disappear. So you can decide which one of these it is that you want to do. If you're wanting to maybe build triangles between that 72 and these two other new points, then you're obviously going to want to keep those points. In this case, we actually don't need them, so I'm going to put a 1 there. Okay. So now you can see this kind of cool effect that we've created. And this is looping over all the primitives, so it's giving us, it's doing this on every single primitive. Even here, it's creating nice, triangles where the, at the top where that was already triangulated, now we're getting 3 points. So it, the actual, this function is quite versatile. Okay, but what if we want to run the same thing, but maybe just slightly different on each one of these primitives? This becomes a little bit difficult to do, just in the loop. So instead, we're going to return this into a function. So let's do this. Right. So how are we going to define a function? The syntax almost looks like we're running a function, except instead of filling in just constant arguments, we're actually defining each one of these. So it's almost going to look a lot like this. Okay. In fact, let me just, I'm going to hit F1 on one of these functions just to remind you sort of what our help card looks like, because this is very much like what we're going to be doing. Okay. So you see we have a type, we have a function name, and then we have our arguments. Okay. So this is what we're going to be doing here. Now remember, just like any block, this entire section needs to be tabbed in, okay, and then encapsulated in the curly brackets. So here we're going to define our function. Now we define what is returned, and what we're going to return, since we're creating a new primitive, it kind of makes sense that we return this primitive number, this new primitive, because the user who's using this function may want to do something with the newly created primitive. So we're going to create an integer. This is basically saying what we're going to return from this, and the class of what we're going to return is an integer. Okay. Then we feed it the name of our function. So I'm just going to call it my function. Okay. And then we're going to give it the list of arguments. Now, if we look across our function over here, what are the type of things inside of here that our user may want to be able to control? Because remember, they won't necessarily have access to everything inside of this. You don't want, even if it's you who is using your own function, you don't want to be fiddling with the inside of it really. You're supposed to be promoting some of these controls to the top level of this function and then just simply running the function. So we look inside of here at all the things that we're going to want to be different. So this bias, for example, is something that I would like to promote because I would like control over where we place that point. We also are going to need to let the user feed the primitive number in, because we're currently running over primitives and we're feeding it at primnum, but maybe the user wants to run it not on our currently processed primitive, but maybe all of its neighbors, something like that. So we have to access this value in the top level of the function. And the final one that I would like to promote is this type, because maybe our user does not want a closed polygon, maybe an open polyline, or a sphere primitive or something. Okay. So those are the three I'm going to do. So let's start with the primnum. So here we define the type, and then we give it a keyword argument name. So int, and then let's just call it primnum to keep as simple as possible. And then I put a semicolon, right? So this is defining the name of it. Our user will input in this position of this function. They will input that argument, and that argument will be fed into the function. Okay, which means that everywhere where we have @primnum, instead we want to just replace it with a variable reference to this variable. Okay, so in this case, because it's primnum, we're just going to take away the @ sign. Okay, then we wanted this this bias over here. So this is a float, so we're going to define float, and we'll just call it bias. So that means we want to replace this with the word bias, so that it references the value that is put into this position. Okay, and then the last one was our type, which is a string. So we just type string type. Okay, we're just keeping these names simple. You need to keep them simple so that your user actually knows what to do. And then we open our block with a curly bracket and close the block with a curly bracket. And obviously over here, we just need to replace this with the word type. Okay. So there we are. So there's our function, but something is complaining, right? Now you'll see, we're going to talk more about errors and warnings and stuff in future lessons, but you'll see here the green squiggly line is kind of saying, okay, well, something's not necessarily broken, but it's just not quite what we expect. This is a warning, not an error. But it says that not all code paths in the function are returning a value, okay? Now remember, we're saying to it, well, we're returning an integer, but actually nowhere have we told it what we're returning. And remember, we covered return as a function, and from inside of a user-defined function, you can just return. Okay, you can return with no value. That is allowed, but then this would be void instead of int. But what we know, we want to actually return a value. What we want to return is this primitive number, just because it's going to be more useful for the user to have access after they've run this function, to have access to the primitive number of the primitive that we just created. So we just say return, and we put a space, and then the name of the variable that we want to return. Okay, and now when we click away or hit insert, you'll see that warning goes away. So everything is functioning just fine, but you'll see that nothing has changed. Like it's as though this is disabled, because this function is no longer actually being run. This has been defined. So in the same way that we can run the remove prim function, well, now we can run our own user function. So we can say my function and then feed it the arguments. Okay, so we need to give it a primitive number. So we say @primnum. We need to feed it a bias. So we say 0.5. And we need to feed it a type. So we say poly. Okay. And there we go. Now we are actually running this function. Okay. And remember, it is returning something. It's returning a primitive number, so we can even store that. We can say I@pr equals, and then my function. And then we can have a look in here, and we'll see that PR, okay, so PR is returning 0 because every time it's creating this new primitive, according to it's primitive 0. So maybe that's not such a useful function over there. In fact, we can fix that. We can just take it away and just make this function void, which will then obviously complain over here that we're trying to store it. But if we take that away, it'll be fine. Okay. So there we are. Now, one thing, I mean, to run it this way, where we just define this whole thing and then run it, is sort of more work than it's worth. I mean, you know, if you're going to run it just once, it's kind of pointless. You might as well just, you know, run this code. But what if we wanted to put it in something like a more kind of complex loop than just, you know, running it perfectly and recursively every single iteration? So let's start with something like an if. Okay, so we say if, and then we do maybe, let's say, a random @primnum, and we'll multiply this by a seed, 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 and then we'll say greater than 0.5. So about half of the primitives will perform this function. Okay, so some of them are going to completely ignore what we're telling it to do, and others are going to run the function. Okay, but what if we instead wanted to, because that we could just put in this line, we could just kind of say if, if this condition, then run this, but otherwise just skip it. So nothing here is particularly fancy, but now what if we put an else, and we run this exact same function, but what if we wanted to maybe feed it a different bias? Okay, so let's get a bit fancy. Let's put this bias in an actual a channel reference. Okay, but remember what I said, we don't want to repeat any lines of code, and ideally what I'm wanting to do is have the same bias in here, but maybe the inverse amount, so 1 minus, which means that some of them are going to be clockwise and others are going to be anti-clockwise. Well, we never want to repeat any lines of code, so actually over here I should come in and define a float called bias, where I feed it our channel reference, and then in here we just simply call our function, well, our variable. So that is the proper way that I was talking about earlier that you should try and do, so that you're never, because it's so much lighter and easier, like almost free for it to call this variable. But to run this function again and again is taking memory. Okay, so once I click away, you'll see it jumps back to kind of our original, but that's because our bias is set to 0. Now watch what happens as we slide this function. You see we're controlling where along that line our point is drawn, and you see some of the polygons are rotating clockwise and others are rotating anti-clockwise. Okay, and in fact if we want to make this one little bit cooler, if we change it to smooth shaded and just maybe drop down a fuse node, so that when they're all together then it forms a nice sphere, like a perfect sphere, but then as we slide we break and then we reform. Okay, so that's pretty cool. You can get some kind of crazy like motion graphics effects out of this, or like really fractal things. I mean, you could run this recursively, and as these shrink, then each polygon splits again and splits again, and so you can get cool fractal motion graphics effects. Yeah, so you see here we're able to kind of repeat this function without having to repeat lines of code, but it's not just a straight loop. We're not just running this identical inside of a loop. Instead we're doing something different. Okay, I mean, we could, even the one of them we could run with different, so one is a polyline and the other one is polygon, or some, something like that. I mean, that's a bit weird, but maybe that's exactly what you want. So yeah, or we could do it on a different primitive or something like that. So sometimes you're going to want to actually have this entire line, block of code run, but with different arguments. So having to repeat the code several times in every single if and else, and then change little bits of it. This is the much simpler and smarter way to do it. I mean, you can see, we can actually just see all of our lines of code within here. Whereas if we had to repeat this would just start getting out of hand. All right. So that'll do it for this lesson. And then next week we'll move on to some other cool, Vex advanced functions. We're going to talk about strings and like regex, and also how to do error handling and that type of stuff. So yeah, I hope you guys have enjoyed, and I hope you're following up to this point, and we'll see you guys in the next lesson.